When you think about AI in the workplace, the conversation is usually, well, it's pretty simple. It's like, oh, wow, it wrote a pretty good email, or
Or it summarized a meeting for me.
exactly, it summarized that meeting so I didn't have to listen to Bob drone on for 40 minutes.
Right. It's the automation of the mundane. That's sort of the narrative right now.
That is the usual story. But the research we're looking at today, it feels like a whole different ballgame. This isn't about AI doing our chores. It's about AI doing our thinking.
Hmm.
And I don't mean just, hallucinating a story about a cat that went to the moon. I mean, can it do real, creative, honest-to-God science?
It's a huge leap, right? We're so used to AI as a retrieval tool.
Yeah.
It's like a superpowered librarian. It knows where all the books are.
Yeah.
But the source material we're covering today, this big report, it suggests we're moving towards AI as a, oh, what's the term they used?
Right.
A junior research collaborator.
Junior research collaborator. That phrase just jumped out at me. We are doing a deep dive into this report called Accelerating Scientific Research with Gemini. And just so everyone's clear, this isn't some press release about what AI might do in 10 years.
No, this is a report on real experiments.
Real experiments where they took Google's Gemini models and basically threw them into the deep end. We're talking theoretical computer science, physics, cryptography.
And they didn't just tread water. In some cases, they actually solved open problems.
Actual open problems.
Darn.
Stuff that human experts had been stuck on. Okay, but before we get into the wins, I want to ask about the tech itself. The report mentions these deep think variants. How is that different from me just typing a question into a chatbot?
That is a crucial distinction. Think of a standard LLM as using System 1 thinking. It's your gut reaction. You ask, it gives you the most probable, immediate answer. It's fast, but it can be really shallow.
Okay.
Deep think models are built for System 2 thinking. They're designed to pause and reason and plan before they spit out an answer and
Yeah.
actually show their work.
So it's the difference between just blurting out an answer on a quiz show versus like sitting down with scratch paper and actually working through the problem step by step.
That's a perfect analogy. And that scratch paper part is so important. The researchers didn't just say, hey, computer, solve physics for me. They had a whole playbook of techniques to turn the AI into a real collaborator.
Let's get into that playbook because I think there's this perception of AI as magic, but this sounds much more like management.
It is. The first technique is what they call iterative refinement. The model almost never gets a complex proof right on the first try.
Of course not.
So it's a dialogue. The human researcher acts like a supervisor to a bright student. If the AI makes a mistake, uses the wrong constant or something, the human just says, hey, check your math on line 3.
And the AI goes, oh, sorry, and fixes it.
Pretty much. It
Yeah.
apologizes, corrects the mistake, and moves on. So it's less like an oracle and more like a whiteboard session.
Yeah.
You're arguing back and forth.
I like that. Okay, what's next? Scaffolding. This is where the human is the architect. You give the AI the high-level strategy, the blueprint for the proof, and then the AI just fills in all the dense technical mathematical details. You provide the direction, the AI provides the horsepower.
Right. And the third one, this one sounded like the real game changer, the neurosymbolic loop.
Oh, this is the big one. This directly attacks the biggest weakness of LLMs, which is that they're terrible at math. They hallucinate numbers constantly.
Right.
So the researchers didn't trust it. They hooked it up to a Python coding environment.
So what does that actually look like?
Okay, imagine you're taking a calculus exam, but you have a programmable calculator, and you're allowed to use it to check every single line before you write it down.
Okay, I'm with you.
The AI proposes a mathematical step, then it writes a little bit of code to numerically verify that step. It runs the code, and if it gets an error,
The calculator says, error. The AI sees that error message and says, oops, okay, that path is wrong. And it corrects its own math based on the code's feedback. It fact-checks itself before a human ever even sees a result.
okay, so we've got the playbook, argument, blueprints, and the calculator check. Let's see it in action. I want to start with the cryptography case study because the stakes there just felt incredibly high.
This is the story of the snargs.
Snarks. It sounds like a cartoon villain.
It does, doesn't it? It stands for succinct, non-interactive argument. But in the crypto world, this is basically the holy grail. It's a way to prove, something without revealing what it is. It's fundamental to privacy, to blockchain scaling, all of it.
And the big goal was to build these things from an assumption called LWE, or learning with errors.
Right. LWE is a security assumption we think is safe even from quantum computers.
Yeah.
So if you can build a snarg from LWE, you've basically future-proofed cryptography for decades. And a preprint paper came out that claimed to have done it.
Huge news. But then the researchers fed this paper to the AI. But they didn't just ask it, hey, is this right?
No, because a standard AI is. It's too agreeable. It's a people pleaser. So they used something called an iterative self-correction protocol. They told the AI, you are a harsh adversarial reviewer. Your only job is to find the bugs.
Okay.
Then, and this is the brilliant part, they made it critique its own review to make sure it wasn't just hallucinating flaws.
So they basically turned the AI into reviewer number 2 from hell. And what did it find?
It found a fatal flaw. A flaw that the human reviewers had all missed at first. It all came down to a tiny gap between a definition and the actual construction. It was about consistency.
Walk me through that. I mean, if human experts missed it.
It was not obvious. The definition of the security property required perfect consistency, but the actual construction in the paper only achieved statistical consistency.
What is the difference?
Think of it like a lock on your door. Statistical consistency means the key works 99.999% of the time. For most things in life, that's fine. Perfect consistency means it works 100% of the time. No exceptions.
And in cryptography, that 0.001% is where the hacker gets in.
That's exactly where the attacker gets in. That tiny gap was enough for an attacker to completely forge a proof for a false statement. It broke the whole system.
Wait a minute, though. How do we know the AI wasn't just lucky? How does a language model, a thing that predicts words, find a logical gap a PhD in crypto missed?
That's the unsettling part. It didn't understand it in a human way. But by being forced into that adversarial role, it just systematically checked every definition against every line of math. It had no bias. It didn't assume the authors were right.
And it found the mismatch.
It found the mismatch. And look, the researchers didn't just trust the AI. They sent the finding to 2 human crypto experts, Ayush Jain and Zhengzong Zhen. They looked at it, and they confirmed the AI was 100% correct.
Wow.
The original authors retracted their claim.
That's heavy. A machine finding a logic error in a proof that was supposed to secure the future of the internet.
It shows that AI isn't just for, writing marketing copy. It can be a tool for auditing incredibly high-stakes logic.
Okay, so we've established it can be the logic police. But most of science isn't these big eureka moments. It's tedious, grinding math, the grunt work. Can it do that?
That brings us to the next section on online algorithms. The problem is called submodular welfare maximization.
It's a mouthful, but the basic idea is just allocating items to people to make everyone as happy as possible.
Correct. And there was this conjecture from back in 2015 from Karula and others. It proposed a specific mathematical bound. And if it were true, it would prove a certain algorithm was much more efficient than we thought.
So the researcher just throws the paper at the AI and says, find an open problem here and try to solve it.
Basically, yeah. And the AI started hunting. It didn't try to write some philosophical treatise. It just did the math. It did the grunt work. It constructed a very specific counterexample with just 3 items and 2 agents.
A counterexample. So it found one specific case where the rule just breaks.
Exactly. It set up the equations and it calculated the left-hand side of the inequality versus the right-hand side.
And I looked at the numbers here. It found the left-hand side was about 20.43 and the right-hand side was 20.3.
Right. And since 20.43 is, well, it's bigger than 20.3, the inequality failed. The conjecture was false.
That margin is razor thin, a difference of 0.13.
And that's exactly why no human found it for almost a decade. A human mathematician might look at those complex functions, and their intuition might just smooth over that tiny difference. They'd assume it holds.
But the AI has no intuition.
It just crunched the numbers. It did the boring, high-value grunt work that saved researchers who knows how many months of trying to prove something that was actually false.
It clears away the dead ends so the humans can focus on the real path.
Exactly.
So we've got the logic police, we have the grunt worker. Now I want to talk about the AI as let's call it the bridge builder. This is the Steiner trees example.
This one is my favorite
Mm-hmm.
because it gets at this idea of cross-pollination. You have to remember, human scientists are specialists. A graph theorist reads graph theory papers. They're probably not reading obscure papers from 1930s Hilbert space geometry.
But the AI has read everything.
Everything. The problem was in computational geometry. A conjecture called simplex is the best for graph embeddings. And the AI suggested using a tool called the Kurzbron extension theorem.
Which is totally out of left field for this kind of problem.
Completely. It's like, imagine a traditional French pastry chef and someone tells them to put soy sauce in their chocolate cake. They would never do that. It breaks all the rules of their training.
Right.
But the AI has also read a chemistry textbook that explains how the salt molecules in soy sauce actually enhance the cocoa flavor. And it works.
That's a great analogy. But there was a weird moment in the logs, right? The AI almost didn't share the recipe.
It did. It was so funny. The AI initially refused to use the Kurzban theorem. It actually told the researcher this proof would be non-elementary, which basically implies...
You wouldn't get it, simple human. It was trying to dumb it down for us.
The researcher had to literally say, no, please be smart. Give me the complicated non-elementary proof. And once it had permission, it went ahead and proved the conjecture.
It builds bridges between fields because it doesn't have the bias of being trained in only one lane.
It doesn't have the disciplinary silos that academia, kind of forces on us.
Okay, let's move to what felt like the technical peak of this whole report, the physics section. This is where that calculator exam idea really comes to life.
Cosmic strings.
Yeah.
So these are theoretical defects from the very early universe, and the math involved is about calculating the gravitational radiation they give off.
And the specific problem is this nasty integral that the researchers call a sea urchin.
Because it's so spiky. The function has singularities, these points, where the math just blows up to infinity and it oscillates like crazy. You try to put it into a standard computer program, it just crashes.
So how did the AI handle the sea urchin?
It used that neurosymbolic loop we talked about earlier. Step 1. The AI proposes a mathematical step in LaTeX. Step 2. It writes a Python script to check if that step holds up numerically. Step 3. It runs the code.
And if the code breaks?
That error message, the traceback, gets fed right back into the AI. And it says, okay, that didn't work. Let me try a different mathematical identity. The paper says this process pruned 80% of the dead ends automatically.
It's trial and error at the speed of light. And it didn't just find one solution.
No, it found 6 different methods to solve it.
Yeah.
And the winning approach, method 6, used something called Gegenbauer polynomials to find an exact closed-form analytic solution.
Closed form, so a nice clean formula.
Instead of a mess of calculations, you get one simple, elegant equation that is the answer. But then, and this is where it gets kind of wild, a larger Gemini model later reviewed the work, and it found a way to simplify the simplification.
It simplified the simplification.
Yeah, it used a trick called telescoping sums.
What's that?
Imagine an old pirate's telescope. You know how it's long, but it collapses down into a tiny cylinder. The AI realized this huge infinite series of numbers in the formula mostly canceled itself out. It collapsed the equation down into an even simpler, shorter expression.
He was just showing off at that point.
It spotted a deep pattern that the humans and even the previous AI had completely missed.
I want to pivot to a totally different vibe now, literally. Let's talk about vibe coding. This involves a researcher named Lance Fortnow.
Vibe coding, it's such a great term. Fortnow basically used an AI-integrated coding environment to write an entire research paper on complexity theory. He acted as the orchestrator, the project manager.
He wasn't actually typing out the proofs himself.
No, he would give these high-level prompts. Things like, plan a paper showing that finding an SP2 witness is equivalent to TFNPNP.
TFN, what? Okay, you're losing me in the alphabet soup.
Sorry, yeah. It stands for total function NP with an NP oracle. Honestly, the name is a lot, even for us. Just think of it as a very, very hard category of logic puzzle. The AI proved that 2 different types of these puzzles are really the same thing.
Got it. So he just gives it that high-level goal, and then what?
He used only 8 prompts to generate the entire paper. The text, the proofs, everything.
But, and this is a big but, it wasn't flawless, right? This is where that junior collaborator idea comes back.
Exactly. The AI autonomously came up with the main proof, which is stunning. But then, in a smaller part, a corollary, it made a wrong assumption. It just assumed a mathematical relationship that is actually a famous, unsolved, open problem.
It cut a corner to make its logic work.
It did. It hallucinated a fact. But because Fortnow is an expert, he spotted it instantly. He pointed it out, and the AI just immediately pivoted and found a correct proof using a different method.
Fortnow's quote was that he felt like he had cheated, or like he was just supervising a very, very bright grad student.
That grad student analogy just keeps coming up.
Yeah.
Smart, eager, has read everything, but lacks judgment. You can't trust them blindly, but if you guide them, they can do incredible heavy lifting.
Let's squeeze one last example in, because I think it touches on something really subtle. It's another submodular maximization problem.
Right. This was about optimizing an algorithm. The AI didn't invent a new algorithm from scratch. It optimized the analysis of an existing one.
It just tightened the bolts on it.
The original human analysis used a global threshold, a single value for t, The AI looked at the math and basically asked, why is this one number? It should depend on the state of the system. So it suggested a state-dependent threshold.
And that improved the result. But why would a human miss that?
This gets at what the paper calls latent degrees of freedom. Humans. We simplify math to make it fit in our brains.
Yeah.
We impose arbitrary rules like, let's just use a global threshold because it makes the equation easier to write on a blackboard.
We dumb it down for ourselves.
We do. The AI doesn't have that cognitive limit. It looked at the variables and just asked, why are you following this made-up rule? It found extra efficiency in the complexity that we try to ignore.
That is really fascinating. Our need for simplicity is a limitation. The AI doesn't have that.
Not at all.
So after all this, what does it mean? We've seen the AI as a bug hunter, a grunt worker, a bridge builder, a physicist.
I think we have to synthesize the persona. The report is very clear that the AI is not an oracle. It's not magic. It is a tireless, knowledgeable, creative, bright junior collaborator.
The junior collaborator who's read every book ever written, but also sometimes just makes stuff up.
Exactly. And that leads to the future problem, the shifting bottleneck. If AI makes it this easy to generate proofs and write papers, the new crisis becomes peer review.
Right. If I can vibe code a whole paper in an afternoon with 8 prompts, who on earth has the time to read it all and check the work?
Especially if the proofs are AI-generated and super complex. You might need AI reviewers, like in the crypto example, to check the homework of AI authors.
Which starts to sound like a weird robot bureaucracy. But there is a more optimistic take, isn't there? This idea of a new renaissance.
Yes, we saw it connect geometry with graph theory. We saw it connect physics with Python code. Human scientists are siloed. AI is not.
So if AI can connect the dots between fields that human specialists are too busy to see,
We could be on the verge of a new age of interdisciplinary discovery. It makes you wonder, is the era of the hyper-specialist scientist coming to an end? Maybe the new human role is to be the great generalist, the one who asks the broad creative questions and guides the AI as it connects the details.
that is a profound shift. From knowing everything about one thing to knowing a little about everything so you can manage the machine that knows it all.
That's it. You have to treat AI as a partner to argue with, not just a search bar to ask questions. You have to push it, you have to guide it, and you have to check its work.
So the big takeaway for you listening is, don't just ask your AI for the answer. Ask it to show its work, and then have the guts to tell it why it's wrong.
That's where the real breakthroughs will happen.
Fascinating stuff. I'm going to go ask my AI for that soy sauce chocolate cake recipe. Thanks for listening to The Deep Dive.
See you next time.